For force identification, the first step that we're going to do is to draw a picture, identifying the object of interest, and drawing a closed curve around that object. The reason we're drawing a closed curve is we are looking for points of contact. Most of our forces are contact forces, and so those forces are going to be associated with points of contact. For naming and labeling each force, that means that we're going to give a name for the force, and we're going to say what symbol we're going to use to represent that in our diagram and in our calculation. We're also going to name and label the field forces. Our field force is going to be the weight. And lastly, we want to make a note of the velocity and acceleration. This is important because some of our forces act relative to the direction of the velocity, and the acceleration is going to be important for setting up our coordinate axes. The next step is to draw the free body diagram. To make a free body diagram, we first do the force identification, then we draw our coordinate system. You're going to orient your axes so that they align with the acceleration vector, but if the acceleration is 0, align it with the surface or whatever is convenient. Make sure that you model the object as a particle at the origin. Nothing else is acceptable. It has to be a particle. Draw the velocity and acceleration vectors off to the side. Use squiggly lines so that you don't mistake them for force vectors. But again, it's important to include these in your free body diagram because we're going to use them to help decide what the directions of some of the force vectors are going to be. We're going to draw all the force vectors. You can check them off the Force ID as you go. Make sure that you have accounted for each one. Our force vectors need to point radially outward. The tail of each force vector should be on that particle at the origin, and any force vectors that are not aligned with the axes should be broken up into components. So to double check, your complete free body diagram includes the coordinate system with the particle at the origin, all of the force vectors, and the velocity and the acceleration. Once you have found the free body diagram, you're going to use that to find Newton's second law equations. Newton's second law says that F equals ma, and we're going to break that up into x and y components. So we're going to look at our free body diagram, and we're going to find all of the forces that have components in the x direction and include them in the with the x components. We're going to use plus and minus to account for the directions. Notice that these are not vectors anymore. These are vector components, and as components, they do not have the overhead arrows over them. We're also going to leave the forces in general terms. We'll leave weight as W, friction as F, and so forth, and we'll substitute in later. We'll repeat the same process for the y direction. Once you have the equation in general terms coming from the free body diagram, then you can substitute in your expressions for particular forces. Drag, weight, the frictional forces have specific expressions that you can plug in, and then you will simplify and solve the system of equations. At this point, it's an algebra problem. If you have a multi-body problem, if you have multiple interacting objects, you're going to draw a separate free body diagram for each object. In particular, you're going to make note of the action-reaction pairs of forces and the acceleration constraints. If the two objects are stuck together, they will likely have velocity and acceleration magnitudes that are related. And if you have a system that includes ropes or pulleys, we're going to assume a massless, frictionless pulley and a massless, inelastic rope. A massless, frictionless pulley requires no effort to get it to move, so we can ignore the effect of the pulley other than to redirect the rope. For a massless, inelastic rope, a massless rope also requires no effort to move, and so it won't affect the system. It won't change the tension. And basically that allows us to treat the tensions at either end of the rope as a pseudo action-reaction pair of forces. The two tensions have equal magnitudes because the rope is massless, the pulley is massless. Because the rope is inelastic, because the rope doesn't stretch, we can also say that we'll have that acceleration constraint that will have the same magnitude of the velocity and acceleration at either end of the rope. This gives us connections between the free body diagrams for each object, the Newton's second law equations for each object, and then we'll be able to combine all those together to solve the overall behavior.